Module 4 Plasma arc machining. Introduction. Plasma arc machining is a material removal process in which the material is removed by directing a high velocity jet of high temperature 11,000 to 30,000 degree ionized gas on the workpiece. The relatively narrow plasma jet melts the workpiece material in its path. Because of the high temperature involved, the process can be used on almost all materials, including those which are resistant to oxy-fuel gas cutting. Plasma is a mixture of free electrons, positively charged ions, and a neutral atoms. It can be obtained by heating a gas to very high temperature so that it is partially ionized. The plasma touch confines the plasma forming gas in an arc chamber, and arc supplies a large input of electrical energy. The central zone of the plasma reaches a temperature of 15,000 degrees Celsius and is collectively ionized. Much of the heating of the gas takes place in the constricted region of the nozzle duct, resulting in high velocity gas exit. Equipment. Figure shows a typical setup of plasma arc torch for cutting. A high frequency spark is used to initiate a pilot arc between the tungsten electrode cathode and the copper nozzle anode, both of which are water cooled. The pilot arc is then cut off, and the external arc generates a plasma jet which exits from the nozzle at near sonic velocity. Water injection is sometimes used to assist in confining the arc to blast away the scale and to reduce smoke. Greater nozzle life is also reported for torches of the water injection type. The plasma jet heats the workpiece by bombardment with electrons and by transfer of energy from the high temperature, high energy gas. The heat is effective in cutting the workpiece to a thickness of 50 mm. Cutting to a greater depth depends largely on gravity flow or forced flow of the superheated molten metal, except for oxidation assisted cutting. The equipment can be used to machine a wide range of materials and thickness by suitable adjustments of the power level, gas type, gas flow rate, traverse speed, and flame gas. This is a diagram of plasma arc machining. DC power supply, tungsten electrode, plasma forming gas inlet, cooling water inlet, brass torch head, copper nozzle, transferred arc, standoff distance, and workpiece. Selection of gas. Any gas that does not attack the tungsten electrodes or the workpiece can be used. Carbon and alloy steels and cast iron are usually cut with a mixture of nitrogen, hydrogen, or with compressed air. Stainless steel, aluminum, and other non-ferrous metals are cut with mixtures of argon, hydrogen, or nitrogen, hydrogen. Typical flow rate of the gas is 2 to 11 cubic meter per hour. Direct current rated at about 400 volts and 200 kilowatt output is normally required. Arc current ranges between 150 and 1000 ampere for a cutting rate of 250 to 1700 millimeter per minute. Non-thermal generation of plasma. The method of heating the gases by first ionizing them is one of the most popular methods of generating hot plasma. This can be done either by applying a suitable electric field across the gas column or by exposing the gas to ionizing radiation, the latter method being very uncommon. Where gases are heated by an applied electric fluid, an igniter supplies the initial electrons which accelerates in the field before colliding and ionizing the atoms. The free electrons in turn get accelerated and cause further ionization and heating of the gases. The avalanche continues till a steady state is obtained in which the rate of production of the free charges is balanced by recombination and loss of the free charges to the walls and the electrodes. The actual heating of the gas takes place due to the energy liberated when free ions and electrons recombine into atoms or when atoms recombine into molecules. The bonding energy thus liberated is manifested in the form of kinetic energy of the atom or molecule formed by the recombination. It is thus clear that the heat content of the molecular gases is higher than that of monoatomic gases. The energy input for such a mechanism is determined by the enthalpy of gas at the required temperature, thermal conductivity of the gas, and loss of energy in the form of radiation.